Good morning, students. In the last video, we have completed the electric intensity due to dipole at a point on the axial line and equatorial line. In both the cases, when you derive the equation for the electric field, it is a vector quantity. Then what is the direction for the electric field, resultant electric field, when you derive an expression for electric intensity at a point on the axial line? When you calculate the electric intensity at a point on the axial line, the direction of the resultant electric intensity is along the direction of the dipole moment, that is from negative to positive charge. And when you calculate the electric intensity at a point on the equatorial line due to dipole, the resultant intensity direction, the resultant electric intensity direction is opposite to the direction of what? The dipole moment. That is from positive to negative. Now these are the two important factors. Then after that we come across the continuous charge distribution. What is that? Continuous charge distribution. Charge distribution. What is that continuous charge distribution? From the properties of electric charges, we know that when the charges are given to the conductor, the charges are resides on the surface of the conductor. So, when the charges are resides on the surface of the conductor, there are large number of charges which are available on the surface of the conductor. Then we come across the distribution of the charges which are continuously on the surface of the conductor. That represents what? Continuous charge distribution. A continuous charge distribution is nothing but a system consisting of closely spaced electric charges. A system of closely spaced electric charges forms continuous charge distribution. From this continuous charge distribution, we come across the three types of the charge densities. That depends on how the charges are distributed on the surface of the conductor, whether they are distributed along the straight line of the conductor or on the surface of the conductor or entire volume of the conductor. Hence, we have got the three types of charge densities for the distribution of the charges. First one is the linear charge density, second one is the surface charge density, and the third one is the volume charge density. Then the name itself indicates that linear. The charges are distributed on the surface of the conductor along a straight line. The surface density, that itself indicates that the distribution of the charges on the surface of the conductor. And third one, if the charges are distributed on the surface of the conductor throughout the volume, then it is called volume surface density. Then we come across linear charge density. Number one, linear charge density. Linear charge density, that is represented by lambda. So lambda is going to be represented for the wavelength, but according to the topic of the subject in the physics, we have got the limited alphabets. Those alphabets are repeatedly used. When you come across the lambda, then it must be understood that linear charge density. When you are dealing the optics and the radiation phenomenon, then we come across that lambda is represents what? Wavelength. So we are dealing the linear charge density, that linear charge density is represented by lambda. Then how to define that lambda? So linear indicates what? The distribution of the charges are along the length of the conductor. So the charges are distributed along the length. Hence, we can represent the linear charge density or define linear charge density. The linear charge density lambda is defined as charge per unit length. What is that? The charge per unit length. Then what is that SI unit? Charge is measured in terms of coulomb and length is measured in terms of meter. That is coulomb meter. Its SI unit is coulomb meter. The SI unit of linear charge density is coulomb meter. Then second one, surface charge density. surface charge density. Surface charge density. Already we have studied in the first topic. So the surface charge density is represented by sigma. So the distribution of the charges are on the surface of the conductor. Hence we can define the surface charge density is defined as charge per unit area. Charge per unit area, that is nothing but charge distributed on the surface area of the conductor. Charge per area, surface area, that is nothing but surface density of the charge. Its SI unit is, charge is coulomb, area meter square, coulomb per meter square. Now this is coulomb per meter because L is divided. So this is nothing but surface density of the charge. If I come across the third one, volume density, charge density, volume charge density, that is represented by rho. Then how it is going to be defined as? The volume charge density is defined as charge per unit volume. Charge per unit volume. If the charges are distributed throughout the volume of the conductor, then we take what? The volume charge density, that is rho equals to charge per unit volume. Its SI unit is charge, volume is nothing but coulomb, coulomb per meter cube. So these are the three types of density of the charges. If the charges are distributed along the length of the conductor, then we come across linear charge density, that is represented by lambda, charge per unit length. Its SI unit is coulomb per meter. If the charges are distributed on the surface of the conductor, then surface charge density sigma is defined as charge per unit area, that is nothing but coulomb per meter square, its SI unit. When the charge is given to the conductor, if the charges are distributed throughout the volume of the conductor, then we come across volume charge density, then that is represented by rho, charge per unit volume. So its SI unit is coulomb per meter cube. Now these are the charge density that is based on the principle of what? Continuous charge distribution. Then after completion of this continuous charge distribution, we enter in the field of what? The main important factor, that is the electric lines of forces or electric field lines. Then after the electric field lines, we come across the electric flux. After studying the electric flux, we come across the Gauss theorem. Then last thing of the topic, application of the Gauss theorem. So then we come across next one, that is electric field lines or electric lines of forces. Then what is the necessity of studying the electric field lines? We are dealing the topic electric charges and electric field. The electric field is the result of what? Electric lines of forces. The electric lines of forces are originated from what? The charge. Hence, wherever the existence of the electric lines of forces, there must be the existence of the electric field. Electric field is the result of what? Electric lines of forces. Electric lines of forces are due to what? Charge. Hence, there is a basic factor for the electric field. We need the electric lines of forces or field lines. The concept of electric lines of forces or magnetic lines of forces was given by the scientist Michael Faraday. According to him, the electric lines of forces, we cannot see the electric lines of forces. When you are not going to see the charge through our naked eyes, it is not possible to see the electric lines of forces. So, the electric lines of forces are purely imaginary lines. There will be no physical existence for the electric lines of forces. We represent the electric lines of forces with the help of what? Geometry. The electric lines of forces are only represented by geometrical lines. Now these electric lines of forces are purely imaginary lines. When the test charge is placed, it experiences a force in that field. It moves in that field. So what is that electric lines of forces? The electric lines of force is a completely imaginary line. When the unit positive charge is placed, it moves in that field. So by using this electric lines of forces, we can represent the electric field. Then what are the properties belongs to electric lines of forces? Then I come across electric field lines or electric lines of forces. Electric lines of forces. Then I come across the properties of electric lines of forces or electric field lines. Now these field lines are imaginary lines according to Michael Faraday. When the test charge or unit positive charge is placed, it moves in that field. That is the definition for electric lines of force. So what is that definition? Electric lines of force is the imaginary line. When the unit positive charge is placed or test charge is placed, it moves in that field. Then what are the properties of electric lines of forces? Most of the students behind the properties of electric lines of forces, just I put the 4 or 3 figures. On the basis of those figures, we can go for what? The properties of electric lines of forces. Then what are those? When you come across the electric lines of forces, there must be the origination. Wherever the origination, it must be end, there must be the termination. Hence, there are two things. One is the origination, another one is termination. So, we have got the two kinds of the charges. One is positive charge, another one is negative charge. Hence, I can put the positive charge here plus Q. I go for pictorial representation. Now, the electric lines of forces are originated from positive charge. The electric lines of forces, these are the electric lines of forces, they are originating from positive charges. Wherever the origination, there must be the termination, then only the completion of the things. So, termination, for the termination, now this is what? Negative charge. The electric lines of forces are terminates on negative charge. We can make, now this is the first property. The electric lines of forces are originated from positive charge and terminates on negative charge. Now this is our first property. Then after this, if I take both are positive charges, second figure, I take both the positive charges or both the negative charges. Now the electric lines of forces are like this. The electric lines of forces are represented like this. So originating. So the electric lines of forces are exerting lateral pressure. Lateral means what? Side. From this figure we can say that the electric lines of forces are exert lateral pressure on each other, which represents the like charges repels each other. We know that the like charges repels. On the basis of electric lines of forces, how to you define that? Like charges are what? Repels. When I take the two positive charges side by side, now these are the electric lines of forces are representation. The electric lines of forces are exerting the lateral pressure on each other, which represents the like charges are repels. If I take third one like this, one is positive, another one is negative charge. The electric lines of forces are like this. Is it clear? From this figure, we can make one more property. The electric lines of forces are contrast along the lengthwise. The electric lines of forces contract along the lengthwise, which represents there is a force of attraction between unlike charges. The unlike charges are attracts. The representation of what? Electric lines of forces that tells that there is a force of attraction between the unlike charges that should be represented in terms of what? Electric lines of forces. If the electric lines of forces are contract along the lengthwise, that represents the unlike charges attracts. If I put the fourth figure like this, Now these are the electric lines of forces which are equispaced and they are in the same direction. A set of electric lines of forces which are equispaced and they are in the same direction represents uniform electric field. A set of electric lines of forces which are equispaced and they are in the same direction represents uniform electric field. Just by seeing the figure only we can make the sentence. Don't by heart the sentence. There are the particular terms. Now this is nothing but exerting the lateral pressure. What is the main term here? Lateral. Now here what the indicates that the electric lines of forces are contract along the lengthwise. Here the term contract, that indicates what? The unlike charges attracts. Then after this, when you are going to see the figure, is any electric lines of whatever may be the closeness of the electric lines of forces, are they intersect? No. You make one more property. The fifth property, the electric lines of forces never intersect each other. By seeing the figure, whatever may be the closeness of electric lines of forces, can you see the intersection of the electric lines of forces? You make one more property. The electric lines of forces never intersect each other. Then what happens if they intersect? If the electric lines of forces are intersect, at the point of intersection, when you draw the tangent, it gives what? 2-2 direction. Hence, we do not have the 2-2 direction for the single point. Hence, we can say that the electric lines of forces are never intersect each other. Then sixth point, sixth property, if the electric lines of forces are crowded, the region where the electric lines of forces are crowded represents what? Strong electric fields. If you want to represent the strong electric field, then how to represent the electric lines of forces? The electric lines of forces are crowded. There are large number of electric lines of forces. They are closely spaced, but there will be no intersection. Then the large number of electric lines of forces represent what? The strong electric field. Then seventh property, if the electric lines of forces are spread wide apart, if the electric lines of forces are spread wide apart, then that indicates what? The weak electric fields. If the electric lines of forces are spread wide apart, that represents what? Weak electric fields. Then eighth property, the electric lines of forces never enters inside the conductor. Already we have studied in the earlier, when the charge is given to the conductor, the charges resides only on the outer surface of the conductor. When the charge never enters inside the conductor, there will be no question of what? Entering the electric lines of forces. Hence we can make the property, the electric lines of forces never enters inside the conductor. The electric lines of forces never enters inside the conductor. So ninth property, the electric lines of forces are smooth curve. The electric lines of forces are smooth curves. If I draw the tangent to the point, that represents what? Direction of the electric field. Now this is the point P. If I draw the tangent for that, that indicates what? The direction of the electric field. Then what is the important phenomenon? That is nothing but 10th property. The electric lines of forces are normal to the surface of the conductor. The electric lines of forces are normal to the surface of the conductor. Now these are the important properties of what? Electric lines of forces. Just by seeing the figure, we can have the 4 properties without biheartation. First property, the electric lines of forces are originated from positive charge and terminates on negative charge. Second property, the electric lines of forces exert the lateral pressure on each other, represents the like charges repels. Then the third property, the electric lines of forces contract along the lengthwise, represents there is a force of attraction between the unlike charges. Then I can make the fourth property just by seeing the figure. If the electric lines of forces are parallel, equispaced and they are in the same direction, represents uniform electric field. Then by seeing the figure, we can make one more property. Whatever may be the closeness of the electric lines of forces, they never intersect each other. It means, next property, the electric lines of forces never intersect each other. Then after that, the closeness of the electric lines of forces. If the electric lines of forces are crowded, then that indicates what? The electric field is strong. Then if the electric lines of forces are spread wide apart, that indicates what? Weak electric field. Then after that, the electric lines of forces are never enters inside the conductor. The next property, the electric lines of forces are smooth curve. If I draw the tangent for the curve at any point, that gives the direction of the electric field. Then last property, the electric lines of forces are normal to the surface of the conductor. Without hurting the properties of the electric lines of forces, we can have the 10 properties just by seeing the figure. 4 property you can write it. You can make the few more properties just by seeing the figures. Is it clear? Yes. Shall I go for the next thing? Then I go for electric flux. So one more term, that is electric flux. That electric flux is related to what? Electric lines of forces. Then what is that electric flux? How it is represented? Then what is the expression for representation of the electric flux? Electric flux, that is represented by phi. When you get the electric lines of forces from the charge, if there is a surface, how many number of electric lines of forces are passing through a given surface normally? That represents what? Electric flux. The electric flux is nothing but number of electric lines of forces passing through a given surface. What is that? The electric flux is nothing but number of electric lines of forces passing through a given surface represent what? Electric flux. Or the electric flux is defined as the number of electric lines of forces passing through normally through a surface. Then how to represent electric flux? Electric flux is represented by phi. Then what is the representation? What is the equation for electric flux? The electric flux is given by, so I go for mathematical representation. Mathematical representation for electric flux. Mathematical representation for electric flux. Now this is the surface. The electric lines of forces are normal to the surface. Now this is nothing but the electric field E. Then, now this is the small surface, I take ds. Total surface area is S, small surface area is ds. I resolve this resultant electric field E into two components. One is horizontal component, another one is vertical component. There will be no effect of the vertical component when we neglect it. It makes certain angle theta. The horizontal component along the direction of the theta, E cos theta. Then the electric flux is given by surface area into normal component of electric field. So electric flux phi equals to, what is the surface area? ds. What is the normal component? E cos theta. Because of this ds, small surface area, small number of electric lines of forces, d phi. Hence d phi equals to ds into E cos theta. If I need total electric flux, phi is equals to sum of d phi. Sum of small number of electric lines of force, electric flux gives what? Total electric flux is equals to sum of ds E cos theta. Hence total electric flux phi equals to sum of, I can make it to be easy spell, EDS cos theta. Now this is your total electric flux. This is a mathematical representation of electric flux. We can say that simply how to remember, sum of EDS sum of EDS, instead of saying that, sum of EDS cos theta. You are going to be scold someone else to be idiot, then you can say that sum of EDS togetherly. We can remember it, sum of EDS cos theta. The total electric flux phi equals to sum of EDS cos theta. Now this is our electric flux. What is that electric flux? Wherever the existence of the electric charge, there is the existence of electric lines of forces. If I take the number of electric lines of forces passing through a given surface, then it is called electric flux. Then mathematically the electric flux is represented by, now this is nothing but the total surface area, yes, I take the small surface area ds, now this is the resultant electric field E. If I split the electric field into two components, one is the vertical component, another one is the horizontal component, there will be no effect of the vertical component, hence it is neglected. The horizontal component E cos theta, that is nothing but normal component of the electric field. Then the electric flux equals to the product of surface area and normal component of the electric field. So ds surface area and normal component of the electric field E cos theta. So ds small surface area, there is a small number of electric lines of forces through it, hence d phi. Then I need total electric flux. Total electric flux phi equals to sum of d phi, that sum of d phi equals to sum of ds E cos theta. To easy spell I can make it to be, this is a scalar factor, hence sum of EDS cos theta, isn't it? Then what is its SI unit? So the SI unit of the electric flux, that is E and ds. E is measured in terms of volt per meter. We come across next chapter, that is E equals to d by dx.